In this video, we're going to talk about probability. You're probably aware of how to do probabilities for simple cases where there's only finitely many possibilities, but continuous random variables can be a little bit more complicated. Imagine we have a situation where the result of something may be any value in a particular range. This could be something like the height of a random person. If we were to ask what is the chance that a person's height is exactly 6 feet, mathematically that answer would be zero. There's no chance that the height would be exactly a value that we pick, because even if we are off by the tiniest little amount, it won't be exactly 6 feet. So what we need to do instead is ask, what is the probability that the person's height is somewhere in a certain range of values? Maybe somewhere between 5 foot 11 inches and 6 feet. In that 1 inch range, what is the probability that we're in that range? So by looking at a range of values, we can get non-zero probabilities from these continuous random variables. In order to actually do any of this mathematically, what we're going to do is introduce what we call a probability density function. So we'll say we have a function f of x where probabilities of some random variable, so we're saying the result of whatever thing we're going to be working with is somewhere in the range from some a to b. And we're talking about the probability that our result is somewhere between a and b. And the whole point of the probability density function is that these probabilities can be actually obtained by integrating this function over that interval. That's what the probability density function means. It's a little hard to actually put this into any other terms. It's a little hard to say the probability density function actually has a particular meaning. It really it's exactly what we're doing here. The only meaning that we can really prescribe to it is as a calculational tool for finding probabilities. But if we want to look at a particular example, let's look at the function f of x is equal to 1 over sigma, so this is a Greek letter sigma, times the square root of 2 pi times e to the minus x minus mu, this is a Greek letter mu, squared divided by 2 sigma squared. That's kind of a complicated function. It looks really complicated. But if we look at the special case of mu equals 0 and sigma equals 1 over the square root of 2, this just turns into f of x is 1 over the square root of pi times e to the minus x squared. And the main thing here is not the constant out in front, but the e to the minus x squared. Recall from the last section, I referred to this function as having something to do with the bell curve. Because if we graph this function, we have something that's very close to 0 and then kind of shoots up and makes a little bump there and then goes really close to 0 again. And it shouldn't cross the x-axis there. We have asymptotes at 0 on both sides. You can say this is our bell curve. When we talk about probabilities using this function as our probability density function, we'd be looking at ranges of values and asking what is the probability based off of this probability density function that our result is somewhere in some range, in this range of values. And so the area under the curve on that range of values is going to be that probability. This is what's referred to as the normal distribution. All the stuff with the mu and the sigma, what mu does is it defines the center point where the bell curve actually maxes out at. If we put a different mu in here, that's going to shift our bell curve along the x-axis. The sigma actually plays a role in defining how sharp, whether this goes up high but is very narrow or if it's really spread out. These are referred to as the mean and the standard deviation of the bell curve. And I'm not going to get more into it than that. This is not a statistics class. We're just kind of getting into some of the basic ideas of how this all works. There are a couple things to note about this function, though, that are very important to it actually being a probability density function. First of all, our function is never negative. We definitely need it to always be at least a positive or non-zero number, or sorry, it should be non-negative. So either positive or zero. It could be zero if there's no probability that our result will come out in a particular range of values. But we don't ever want to have any section of our curve where the area is actually negative, because a negative probability doesn't really mean anything. Probabilities are always between 0 for impossible to 1 being certain. Speaking of being certain, we want to know that the chance that we're anywhere on the real axis is 1. If we pick a random number based off of this distribution, we have a number. If it is in the real number somewhere. That's what we're really saying. We wanted the probability that we get a number is 1. And so we want to say that the area underneath the curve for the entirety of the real line is 1. In other words, the integral of our function from negative infinity to infinity, you put the dx, that has to equal 1. And that's the whole role of the 1 over square root of pi that we have here. Remember, in the last section, we found that the integral of e to the minus x squared from negative infinity to infinity is square root of pi. We have to divide out that square root of pi to get 1 instead of square root of pi. And so that's the whole reason this is even here. And that's the main reason why we cared so much about finding that integral in the last class. Same kind of thing with the sigma and the 2 that are out here. That's just kind of changing, or it's basically making sure that if we integrate this e to all this stuff, we get a 1 overall. It's canceling out anything from integrating this particular function. But we need these two pieces of information to be true for this to be a probability density function, for it to actually give us a probability. And those are important factors that we're going to take into everything that we're going to do in this section. Because what we're doing here is not looking at just one random variable, we're going to look at 2. Because we're going to be moving from integrals to double integrals. Most of the time we kind of want to think of this as being the x and y coordinates of a point, and we say that the result is going to be, we're going to say we want the result to be in some region D. So what is the probability that our result is going to be in that region D? And in order to get that, we're going to introduce, as you might expect, a probability density function. Though here we're going to call it a joint probability density function. Or I think the book just refers to it mostly as a joint density function. But this is going to be a function of 2 variables, f of x, y, where the probability that our result for x and our result for y happen to be in this region D is equal to the double integral over D of this function of x and y. And again, there's not really any any other interpretation we can give it. It's mostly just a calculational tool for computing these probabilities. And in any of the situations that we're going to be looking at in this class, this probability density function is just going to be given to you, or at least be something that we can derive fairly easily from how they mention it. But there are two pieces of information that we need to have true. First of all, we want this probability density function to be non-negative. We don't have any negative probabilities because that doesn't mean anything to us. Secondly, the integral over all of R2 of all of the plane has to equal 1. Because again, the probability that we get any result whatsoever, that a result turns out to be some point in the plane, has to be 1. It has to be certain that we actually got a result in the first place. So any function that we choose has to satisfy these two conditions in order for any of this to make any sense. But those are the only conditions that we have for our probability density functions. Now there is one particular situation that we do want to note. We can talk about two events being independent. And that means that the result of one does not affect the result of the other one. In terms of our probability density function, this actually corresponds to the case where our function f of xy is actually the product of a function of x times a function of y. Because that means that if we actually compute these probabilities, so the probability that are, let's say if we're going over some rectangle R, so we have R here is some AB crossed with CD. The probability that our result is in that rectangle, we can just set this up over this rectangle pretty easily as the probability of, so let's just go ahead and write it, g of x times h of y dy dx. Because we're dealing with just numbers as our limits, and our integrand actually is just the product of a function of x and a function of y, we're able to just split this up pretty easily. We have the integral from a to b of g of x dx times the integral from c to d of h of y dy. Well, this thing here, this is actually the probability density function for the random variable x. So really we're just saying that the probability that x is between a and b. This one similarly is for y, the probability that y is between c and d. So it's saying that the probability that we're in this rectangle can just be written in terms of the probability of our x being in a certain range and our y being in a certain range. There's not really any intermingling of these probabilities. They don't really affect each other. Now, of course, we're only doing this over a rectangle. If we're not doing this over a rectangle, this doesn't help quite as much because the limits can actually affect the other one. But as long as we're working over a rectangle, it can just split up into probabilities of x and y separately. And that's what we mean by being independent. They're going to use that in some of the exercises to actually to kind of construct the probability density functions. Let's just jump right into some problems. Here's problem 28. They give us a function f of xy, which is equal to 4xy as long as x is between 0 and 1 and y is between 0 and 1, and it's 0 everywhere else. And we want to show that this is a joint density function. It can be the probability function, or the density function for some probability. And then it wants us to compute some probabilities based off of that. And we'll come back to the expected value part in a moment. So first, what do they mean by verify that this is a joint density function? Well, remember, we do have our two conditions. We need to show that, well, first of all, that our function is never negative, and we need to show this integral over everything is equal to 1. Well, hopefully it's pretty easy to see that we aren't going to be negative. If we're not inside the box, let's just draw the box in here. So from 0 to 1 and 0 to 1, this is the only place where our function is ever not 0. And then it's going to be 0 along these edges, but then we're going to be taking the product of two positive numbers anywhere else. And so we're definitely going to get positive numbers no matter what, as long as as x is greater than 0 and less than or equal to 1, and y is greater than 0 and less than or equal to 1. So hopefully that part's really easy to tell. I mean, maybe I'll even say, obviously, f of xy is greater than or equal to 0. The other part's not quite as obvious. We need to look at the double integral of our function over all of the plane. They made it kind of easy on us here because our function doesn't mean anything outside of this square. So really what we're going to be doing is we're going to be integrating over this square. Maybe I'll call it r. So we're integrating, taking the double integral over that square of the function 4xy. Because anything outside there doesn't matter. This isn't too hard of an integral to do, because we are just we're just over a rectangle. We're going from 0 to 1, 0 to 1 of 4xy. We can actually put dy or dx first. Doesn't really matter. In fact, we can even split this up pretty easily. This is the function of, say, 2x times 2y, and so we're actually looking at an independent set of random variables over a square. So let's just actually do that. We'll have a 2x and a 2y. Now you might wonder why I didn't just pull a 4 out in front. Well, what's the integral of 2x? It's x squared. And the integral of 2y is y squared. We put in 1. We have 1 minus 0. So this is a 1 times a 1. We get 1. That's what we wanted. So this is a joint density function for the probability for these two random variables, capital X and capital Y. We don't really know much more than that, but we do have that at least. We are now going to compute two probabilities. First one is going to be the probability that x is greater than or equal to 1/2. Essentially, we're going to do this way. We're essentially going to find the probability that we're in this section. The next one will take x is greater than or equal to 1/2, and y is less than or equal to 1/2. So we'll actually kind of look at this section for the second one, just that little quarter box there. But we compute those probabilities the same way we normally would. So the probability that x is greater than or equal to 1/2 is just going to be the double integral over that half of the box, the part with these cross hatches. Kind of ignoring anything that happens outside of that square, because all of that doesn't matter. I'm just going to call it r for now. But the point here is my x values are going to go from 1/2 to 1. My y values are still going to go all the way from 0 to 1, because there's no restriction on our y values. we're still going to be looking at 4x squared, or sorry, 4xy dy dx. This is actually still independent, so, and we are working over a rectangle, so we can actually split this up. We already know this integral here of 2y from 0 to 1 is going to equal 1. We're just really concerned about this one here. Of course, that's x squared from 1/2 to 1, which means we have 1 minus 1/4, so we get a 3/4. Our other probability, the probability that x is greater than or equal to 1/2, and y is also less than or equal to 1/2, again, is just a double integral. This time, our x values are still from 1/2 to 1, but our y values are from 0 to 1/2. We can still split this up like we did in this last one. So 1/2 to 1 of 2x dx. We the integral from 0 to 1/2 to y dy. Of course, we just keep using the stuff that we found out from before. The integral from 1/2 to 1 of 2x turns out to be 3/4. When we integrate this one, we have y squared from 0 to 1/2. And then when we plug in our limits here, we have 1/4 minus 0. So we have 3/4 times 1/4, or 3/16 for our answer there. Now, what do they mean by expected value? Well, they essentially mean, what if we had this random result? There are a ton of possible results out there, but what result would we expect to get? And it turns out that this question is pretty closely connected to the same idea that we had behind center of mass. If we have a probability density function, we can think of probabilities as the mass of a given region, and while the expected values for our x, so the expected value for x, which I'm going to denote as e of x, because that's the more common notation here. The book actually will denote this by mu1, but it's kind of the averaging of our possible values of x, kind of weighted by the probability of those values. And we also have an expected value for y, which the book is referring to as mu2. And we want to know, how do we compute those things? So the expected value of x is playing the role of the moment around the y-axis. It's essentially the, well, maybe I shouldn't put it that way. What I should basically say here is that the expected values mu1 and mu2 should be essentially the x bar and y bar that we had with center of mass. And remember how we commuted x bar? That was our double integral of x times our density function divided by the mass, which is the double integral of our density function. That was our formula for the center of mass. In the case of a probability, our density function is going to be this f here, this f that we have here. So we're integrating this f both with multiplied by x on the top or without the multiplying by x on the bottom. But one thing that we can note is that we do have the double integral of f over the entire real plane is equal to 1. So here, the bottom, if we're taking the double integral over all of R2 of f, this bottom is always going to equal 1. The top, on the other hand, won't necessarily, at least. So this mu1 or x bar, however you want to put it, really the more common notation here is e of x, is just the double integral over r2 of x times f of xy. And then the same thing for y bar, or m2, or e of y is going to be the double integral over all of r2 of y times f of xy. Just playing the same role as our center of mass or our moments when it comes to probability. And so that's what we're going to do here. When we're trying to find the expected values of x and y, we're going to essentially take this kind of integral that we did here, but we're going to multiply by x and we're going to multiply by y in the integrand, and then do the integration. So e of x, and I know the book doesn't use this notation, but I'm going to go ahead and use that here. We're going to look at the integral. Let me just put r2 here, of x times our function. Our function was 4xy. Of course, we can ignore anything that happens outside our box from 0 to 1 and 0 to 1. So you just go ahead and put 0 to 1, 0 to 1, and then we have our function 4x squared y. And honestly, it doesn't really matter what order we put those in because the limits are the same. We can do the same kind of trick that we've been doing and split this up into multiple integrals, because our integrand is still a product of a function of x and a function of y. So the integral from 0 to 1 of, let's just pull 2x squared out, because we already know what the integral of 2y from 0 to 1 is. This just turns into a 1. This integral, not so much, because integrating 2x squared, we get 2/3 x cubed from 0 to 1. When we plug in 1, we get 2/3. E of y is actually pretty similar. What are you doing there? Keeps wanting to make them straight lines instead of follow my pen. We're taking y times our density function this time. And a lot of this will actually result in the same kind of thing. Instead of having x squared here, we just have an x, and instead of having a y here, we have a y squared. But you can you should be able to see that that's going to result in the same result in this case, because x and y are playing very symmetric roles in this problem. So I'm not going to go through that again. If you want to, you can do that yourself. All right, one last problem, and this one actually is going to be an applications type problem. Not so much just I give you a function and you do some integration. We actually have a problem where we have to read it. So we have a lamp that has 2 bulbs. Each bulb has a type with an average lifetime of 1,000 hours. Assuming that we can model the probability of failure of a bulb by an exponential density function with mean mu equal 1,000, find the probability that both of the lamp's bulbs will fail within 1,000 hours. So our probability here is talking about when are these bulbs going to fail. Now, they are kind of throwing some new words at you. What is an exponential density function? And they don't really tell you exactly where to look this up. This is referring back to Chapter 8. So in Chapter 8, they covered the probability density functions of just one variable instead of the 2 variables that we're working with here. I don't know if you covered that in your covering of Calc 2. But In that chapter, and let me even, yeah, if you want to look back, it's in section 8.5, example 3, they actually derive a formula for it. So there, you can say that our probability density function f of x is going to be, well, it's going to be 0 for x less than 0. So nothing's going to happen until we actually start. So we have a starting point when x equals 0, and our bulb won't burn out before that because we haven't actually started using it yet. And then after that, it's going to be 1 over the mu. Our mu here is 1,000, so 1 over 1,000 times e to the minus x over the mu of 1,000. And this is for any x that's bigger than or equal to 0. That's what they mean by an exponential density function. It's one where there's a fairly high probability at the beginning, and then it decays off over time using an exponential model. And technically here, by this model, there's a finite probability that the bulb will just never burn out. But obviously, that probability decreases over time until there's just really no chance that it's not going to be burned out. Of course, here both the bulbs are following this model. So we have, say, f of x for our first bulb, and we have a similar f of y for our second bulb. But it's going to be the same formula, the same result here. Just with y's instead of x's. Our joint distribution, because these are going to be independent of each other. One bulb burning out is not going to cause the other bulb to burn out. I mean, I guess we could theoretically think in a situation where that might not be true, but here, because they haven't told us anything more, we're going to have to assume that. So we're going to say our joint distribution, our f of x and y, is just going to be the product of these two things. And so that's going to equal, say, 1 over 1,000 e to the minus x over 1,000 times 1 over 1,000 e to the minus minus y over 1,000, as long as both, when x is greater than or equal to 0 and y is greater than or equal to 0. If either one of these is less than 0, it's 0. But honestly, that part we don't really care about. We want the probability that both of the bulbs fail within 1,000 hours. So what are we really looking for there? So now we're actually trying to solve the problems. We're looking for the probability that our first bulb fails, so that the time that it fails, which we'll call capital X, is less than or equal to 1,000. And that the second bulb failing, which we'll call Y, also happens less than or equal to 1,000. We're actually looking here at a rectangle, just from 0 to 1,000, 0 to 1,000. So we can actually set this up as we would a normal rectangle. And then we put our probability density function, which is this fun thing here. I even just copy it in there. And again, it really doesn't matter here which one of these I do first, but we'll have that in there. Now, since these are independent and we are working over a rectangle, we can actually split this up into multiple integrals. We have the integral from 0 to 1,000 of the stuff involving x, times the integral with y, So essentially, we're just multiplying the probability that the first bulb fails within 1,000 hours times the probability that the second bulb fails within 1,000 hours. Both these integrals are going to be very similar. When we integrate 1,000 times e to the minus x over 1,000, remember when we deal with e to some constant times x, we end up dividing the outside by that constant when we integrate. So the function, the e to that constant times x stays the same, but we're going to divide 1,000 by negative 1,000. So that's going to get rid of the 1 over 1,000, but it's going to give us a minus sign. Of course, this exact same thing happens for the y. We get to plug in those values. So first, when we plug in 1,000, we get negative e to the minus 1. Since that's negative, I'm going to put it last. So e to the negative 1 is 1 over e. Then when we plug in 0, e to the 0th power is 1. So, and then we're subtracting a negative, so we have 1 minus 1 over e. The other one's going to be the same way. Get 1 over 1, or we get 1 minus 1 over e. And that result is approximately, say, 0.39957. So around a 40% chance that our bulbs will both burn out before 1,000 hours. In part B, we're going to change what lamp that we're talking about. We're still going to have the same idea for our bulbs, but this time we're going to put a bulb into a lamp with just one slot, and then when that bulb burns out, we're going to replace it with another bulb. And we're going to ask, what is the probability that both bulbs fail within 1,000 hours? So that the first bulb was failed within 1,000 hours, and then when we replace it with a new bulb, that second bulb will fail before that 1,000 hours is up. Now we actually don't need to change our probability density function. What we need to do instead is consider the idea that we're going to take the time that the first bulb takes to burn out plus the time that the second bulb takes to burn out. So we're saying the first bulb burns out within x, burns out after x hours. Second bulb burns out after y hours. What's the probability that the sum of those two things is less than or equal to 1,000? Because if the sum of these two times is less than or equal to 1,000, then that's the same as just putting one bulb in there after the other bulb. What we're really doing here when we do that is considering a different domain other than a rectangular one. So we're thinking here of the region in the plane where x and y are still going to be positive numbers, or at least non-negative numbers, but x plus y is less than or equal to 1,000. What does x plus y is less than or equal to 1,000 look like? Well, sorry, this should be 1,000, not 100. Well, let's graph x plus y equals 1,000. That's going to be a line like that. So we're really looking at some triangular region. Any point in here, if we treat the point, the coordinates of that point, as the death times for two bulbs, that's going to satisfy this condition. If we're outside this region and we still have positive numbers for our x and y, then we're going to not satisfy that condition. And so we're wanting to essentially integrate over this region. Find the probability over that region. So double integral over d, we'll call it d, of our function. When we set that up, we can say we can treat this as a type 1 region where our x's are going from 0 to 1,000, but our y's are going to go from 0 down here up to that line. That line, we just solve x plus y equals 1,000. We solve that for y, so we end up getting 1,000 minus x. We're still going to be integrating the same function. This time the order here matters. We do need to put the dy first. When we integrate it, this first part doesn't really depend on y at all, so we'll just keep it there. So we have that all out in front. And then this part here, the 1,000 e to the minus y over 1,000, we already did that integration a moment ago. That turned into a negative e to the minus y over 1,000. And we're going to take that from 0 to 1,000 minus x. Now we get to plug in our limits. Still have 1,000, still have 1 over 1,000 e to the minus x over 1,000 times, well, I'm going to go ahead and plug in the 0 first because I know with the minus sign here that's going to be the one that's going to be out in front because I'm going to be subtracting a negative 1. So it's going to have 1 minus e to the negative 1,000 minus x. So say x minus 1,000 over 1,000. That got a little messy. I don't know if that was any better. We want to integrate this thing, and that seems maybe a little fun in a sarcastic kind of sense. But I'm going to go ahead and distribute this to all these terms over here. So first we'll have a 1 over 1,000 e to the minus x over 1,000 because all we did was multiply that to 1. But now we're going to subtract 1 over 1,000. And when we multiply these two e's, we end up actually just adding the exponents together. So negative x over 1,000 times, negative x over 1,000 plus x minus 1,000 over 1,000. The x's actually cancel each other out. We get e to the minus 1,000 over 1,000, or really just e to the negative 1. And e to the negative 1 is really just an e on the bottom. So really this whole thing became a constant. It's just a constant that's being tossed in there. Let's actually copy this to the next page so we actually have some room to put it. And we get to do all the integration with respect to x now. Of course, we already dealt with this particular one here. This becomes a negative e to the minus x over 1,000. This part is a constant, so we end up getting a minus x over 1,000 e. We're going to take that from 0 to 1,000. We plug those in here, we get 1 minus 1 over e, because we're just doing that the same way that we did this part here. But then with this term, we have a minus 1,000 over 1,000 e, and then obviously 0 for that one. So these are all the terms we have. We have 1 minus 1 over e, and then this is another 1 over e. So 1 minus 2 over e. Or approximately 0.26424. So basically, if we're allowed to put a bulb in after another bulb, and we want to see whether or not both of them will be burned out within 1,000 hours, that's only a little bit more than a quarter of a chance. All right, so I've gone on maybe a little longer than you'd like me to. These are maybe not the most straightforward examples, but once you get more used to them, you can go through them a little quicker than we have here. But I'm going to leave it here. Feel free to take a look at some of the other applications that the book talks about. Um, Most of it boils down to the same kind of ideas of having some sort of density function. We call them density functions in both cases here, both when it came to masses and when it came to probabilities, and that's because they play very similar roles to each other. In the next section, we will actually look at a different application of double integrals, this time to surface area. But we'll see that in the next videos. So I'll see you there.